Hello, good afternoon, good morning, everybody. We are very glad to have you for this webinar. And we will focus during the webinar on soil carbon in agriculture, and especially on the monitoring, reporting, and verification methods. We are going to introduce this topic, and then we will have some more in-depth presentations. We are working on those issues with collaborations through several projects, a European project which name is CIRCASA on international cooperation for research on soil carbon sequestration, also with the European Climate KIC Knowledge and Innovation Community, and with the French Agency for Environment, ADEME. So how could we monitor soil carbon sequestration is often a question we get. And this is really a timely question when we remember that soil carbon is an issue at the intersect of several international challenges, climate change, food security, and also desertification, land degradation, and biodiversity. So when we want to think about monitoring soil carbon and understanding soil carbon sequestration, we should assess changes in soil organic carbon stocks. This means we need to select a baseline period and a reference land use and land management scenario. Then, in case we introduce a new agricultural practice, the change in carbon stock will result from the difference between that reference scenario and the scenario where we adopt a change in land use or land management. Therefore, this issue of a baseline for the changes in soil carbon stock is quite important. We know that soil carbon stocks are often not in equilibrium, and this is because we have some past land use change. For instance, you may work on a cropland that was maybe 10 or 20 years ago grassland. So in that case, usually the soil carbon stock would decline. And therefore, on this slide on the left, you have a graph which shows what may be a baseline, and assessing this baseline of the soil carbon stock in total carbon per hectare, this is organic carbon, is needed to understand the additional soil carbon storage that may happen after a change in practice. And this is shown here, depicted as a green line, where you would have an increase in the soil carbon stock compared to a decline in the baseline. So the additional carbon storage would not only be the difference between the increase of the soil carbon stock and the past value at the start of the introduction of the practice, but it is also, in effect, the difference between the baseline, which is declining, and the increase in the soil carbon stock. So we would like to underline this because, for instance, we know that baselines may be quite different from zero. They may be negative in terms of relative change in the soil carbon stock, or they may be positive. And in many countries, we do not know exactly what is the mean baseline. For instance, in France, we estimate a range which is between -3.3 up to plus 0.9% per year for the baseline soil carbon stocks. This is for the topsoil, 0.30 centimeter, for the croplands. And we estimate another range, which is in that case positive, from 0.06 to 0.25% relative change per year in the soil carbon stock for the grasslands. So as you realize, both for monitoring a baseline and for monitoring a change after a practice, we need to assess the soil organic carbon. And there are two ways basically to do this. The most used way is just direct coring. We would core the soil, we would measure the carbon content in the soil, and we would also measure the bulk density over a reference depth. As we know, that depth is critical because there are some practices which may change the soil organic carbon content in the topsoil, but actually would also have counterbalancing effects in the deep soil. So if you were to sample only the topsoil, you would get to one conclusion, but if you sample also the deep soil, you may have a different conclusion. So selecting the baseline period, selecting the reference land use scenario, measuring directly the changes in the soil carbon stock over a time period are the classical ways to monitor the change. And the change will be given by the difference between the reference scenario and the scenario with a change in land use or land management. There is ample literature on how to do this, and we could point you to the recent guidelines by the FAO that also describe how to do this in depth. However, this webinar is focused on, let's say, an alternative method, which we believe is quite powerful if we invest sufficiently in that method. And this is to create a soil carbon balance. This soil carbon balance is a balance between the inputs of carbon to the soils and the outputs. So the inputs are organic inputs. They may be derived from the vegetation, they may come as crop residues, they may come as leaf litter, and so on, or exudates. And they may also come as organic fertilizers. This could be manure, this could be also some excretal return at grazing, like dung. And those organic carbon inputs will enter the soil, enter into decomposition, lead to soil respiration, lead to an increase possibly in the carbon leaching, the dissolved organic carbon leaching, for instance. And in this way, the inputs are going to be balanced by outputs. There are also outputs where we harvest the vegetation. So in this system, we are going to remove carbon. And we should know this to calculate, in fact, what goes to the soil in the system. So looking into the balance of incoming and outgoing carbon fluxes can lead you to an estimate of the soil carbon balance. However, as you may realize, this is not obvious, and there are many ways to calculate or to model this soil carbon balance. So let's first look at the case of a cropland. Here we have on the right the way the fluxes are organized with the photosynthesis leading to an increase in plant biomass, with the respiration, which is both from the plants and the vegetation, therefore, but is also from the soil. And the balance in this case will lead to the neat primary productivity, which is the amount of carbon that is accumulated in the vegetation system over a given time period, over an annual time period. Part of this neat primary productivity will be removed by harvests, and there may also be some organic fertilizers applied to the soil that will increase the inputs of organic carbon to the soil. And as we said, we have decomposition, we have respiration, we may have leaching, we may also have some erosive fluxes that can alter the soil carbon balance. So if we look at the fate of the carbon as a cascade, we would start from photosynthesis. We would move into primary plant productivity, which means we would subtract the plant respiration. We would remove the harvested carbon, and then we would get the soil carbon, the input of carbon to the soil. And to calculate that input, we take into account the addition of organic fertilizers carbon. And knowing the input of organic carbon to the soil, we can calculate a soil carbon balance, assuming we have estimates of soil respiration, which is releasing carbon dioxide, and carbon leaching. Obviously, there may be some other minor fluxes, but at this stage, I will not enter into the details. So we should do this for the baseline conditions and also for a scenario where we change the land management or land use. How can we do this is a question, obviously. So we have estimates about photosynthesis from, for instance, remote sensing. Later, the talk by Ceschia will explain this. We can readily measure in the field the harvested carbon, or we could estimate it from a harvest index. We can measure, or we may have statistical data or farm data on the amounts of organic fertilizers that are added. And we can model, knowing the supply of organic carbon to the soil, the fate of that carbon, model respiration, model leaching, and therefore calculate the soil carbon balance. Let's move to a pasture where there are some further fluxes. For instance, we are having here an animal that is grazing. And by grazing, it will create some offtake of the herbage. It will digest that herbage, leading to respiration, so carbon dioxide flux, but leading also to enteric methane emissions. So this is also a carbon emission from the system. And you see that you may have some additions of manures, you may have some harvests, and we should, if we want to really create a balance, consider that part of the carbon will go into dairy products. So there will be exports of carbon from the milk or even from the meat. So this is the balance of the fluxes, and we've been investigating both in croplands and in grasslands, and this is largely an international effort, those balance of carbon through eddy flux covariance that measures the balance of the photosynthesis and of the respiration of the system. So you see here that we have a slightly more complex case with the pastures, where in addition to the fluxes I already mentioned, we should account for the herbage offtake and for the recycling of carbon by the grazers, which leads to application of dung and urine carbon to the system. So we would like to focus during the webinar on the estimates of that soil carbon balance, and we would like to question also with your comments and inputs if we could base in the future monitoring, reporting, and verification on such flux estimates. So during the webinar, we will hear from Gecica on the Tier 3 monitoring, reporting, verification methods at national and project scales for soil carbon. We will hear from Ceschia on how we could combine remote sensing and modeling for such a soil carbon MRV. We will hear from Antonio Bispo on how we could improve our knowledge of the soil carbon stocks to contribute to that understanding of the fluxes and of the MRV. And I will just conclude briefly, and this will lead us to your questions and your comments so that we can collectively make some progress on this topic, which is both important and also quite difficult, technically speaking. Thank you.
Thank you, Jean-François, for this introduction, and thank you everyone for joining this webinar. My name is Gecica, and I'm working at INRA as a soil carbon engineer in a project funded by ADEM and coordinated by INRA. And I will focus on Tier 3 methods for carbon offset projects at national and project levels. So at the national level, the IPCC guidelines offers a 1 to 3 order of methods for greenhouse gas inventories, Tier 1, Tier 2, and Tier 3, and the latest giving the highest precision for estimations. As a reminder, mineral soils and organic soils both contains organic carbon and inorganic carbon. And today we focus on soil organic carbon noted as SOC, which is triple the amount of carbon in the atmosphere in the form of CO2 on a global scale. So the default method, the tier 1, uses reference carbon stocks and stock change factors available in the report. At the second order of method, tier 2, country-specific or region-specific data can be used. This is the case for France, where land use factors have been derived from regional data with the RMQS data, which is a soil surveillance network that will be presented later on by Antonio Bispo. The corresponding reference stocks and stock change factors have to be derived accordingly. Change in mineral carbon stock due to biochar amendment also can be estimated at this level, but not in tier 1. It's also possible in tier 3, the highest order of methods. Here, process-based models and inventory measurements tailored to address national circumstances, repeated over time and driven by high-resolution activity data and disaggregated at sub-national level can be used. These higher-order methods also provide estimates of greater certainty than lower tiers, the tier 1 and tier 2. Also, these methods can be used to model the loss of biochar carbon over time after its application to mineral soils. It also can help to capture other greenhouse gases that have not been taken into account in lower tiers. It can also help to estimate changes to net primary production associated with input of carbon to soil organic carbon pool, as Jean-François mentioned. Few examples of tier 3 application for soil organic carbon stocks change in national inventories. Here, in Australia, they implemented a tier 3 inventory approach based on the use of the FullCAM model. The FullCAM model is a fully integrated carbon accounting model for estimating and predicting all biomass, litter, and carbon and soil carbon pools in forest and agricultural systems. In addition, it accounts for changes in major greenhouse gas and human-induced land use practices. This model is used to estimate management-induced changes in the stock of organic carbon in the first 30 centimeters in areas that are squared 25 meters by 25 meters areas across the country. In Finland, they use ISO 07 soil carbon model as a tier 3 method to report carbon stock changes on forest and agricultural lands, as well as in the cases of land use change. The ISO 07 model is well used, and it has been tested over a large set of data in forests and croplands, and it's used for UNFCCC reporting in several countries as well. Also in Japan, they use the Rothamsted carbon model, ROTC, which was originally developed in the UK, but for the Japan climate and agriculture, the model had to be validated by using long-term field experiments. And it has been found that the model could apply for non-volcanic upland soils without any modification or calibration, except for undersoils and paddy soils, where they had to make few modifications to take it into account for the changes in soil carbon in these type of soils. In the US, they use Dyson ecosystem model to model the stock changes in cropland and grasslands. More precisely, the uncertainty is reducing up to 20% with this method compared to lower tiers. There are methodological developments in France, as we were talking as Jean-François was introducing the use of satellite data and remote sensing in Tier 3 methods, the soil reflectance properties can be used with a spectral model to calculate topsoil organic carbon in the 8 first centimeters. This work is going on at INRA Research Center, and references are provided for papers that have been wrote on this topic. Satellite images can also be used to feed a model, the SAFYE-CO model, which will be developed by Ceschia in a few. This model is developed in CESBIO in Toulouse, also in France. And most of the input data required can be found in the French national databases or freely available at global scale. And for the soil databases, Antonio Bispo will give us more information also about that. New methods also are arising, such as thermal analysis, which is promising. They could allow identify fractions having a residence time of about 20 years. The rock eval tool, the number 6, rock eval 6, RE6 here, is a tool that is originally used in the oil industry and gives the possibility in one sample to estimate for inorganic carbon and for organic carbon within an hour. So it's very quick. Data from long-term bare fellow experiments can also be combined with thermal analysis from the rock eval 6 to quantify the size of centennially persistent soil organic carbon pool. This has been developed by Ceschia, which references on the PowerPoints for you to have more details. And this helps to better calibrate soil carbon models. For example, the ABC-TER method, which is a French participatory approach, combining model and expert opinions at diverse territory sizes, has been improved thanks to the rock eval analysis. In fact, the AMG model is a simple model that have a prediction improved when the optimization of the stable carbon pool is made with the rock eval 6. So it could constitute a standard method to complement carbon stock measurement in soil monitoring program. Other participatory approaches are developed, Maelia for cropland grassland cover crops and carbocage for edges. And at international level, other soil organic carbon estimation methods are available for carbon offset projects. For example, in Australia, with the Carbon Farming Initiative, which is under the Emission Reduction Fund, with two main available methods for soil carbon sequestration. The first one, the methodology determination 2015, estimating sequestration of carbon in soils using default values. So this method, as the name says, uses default values. And the second one, the methodology determination 2018 for carbon sequestration in agricultural system. So these two methods are not the only one. There was another method, the methodology determination 2014, which is now revoked, but had led to the first carbon credit units attributed to the Soil Key Pasture Renovator project. So this was in May 2019, so a few months ago. And the aim of this methodology was to to help develop the voluntary, the carbon voluntary market. So the methodology determination 2018 seeks to overcome the limits that have been underlined in the previous methods by introducing new components and adapting some components from the two, so the 2014 and the 2015 earlier soil carbon methods. This provides proponents with the flexibility to respond to market forces and participate in the emission reduction fund and continue to make land management decisions, enabling them to meet the broader business objectives linked with the carbon market. In the US, there is a carbon management evaluation tool for the whole farm greenhouse gas accounting called Comet Farm. This tool is free, available online, easy to use. And the aim of this tool was to help incentivize carbon offsets in projects, and also for local farmers to improve their management practices. Government programs also can be based on this tool, and the supply chain management as well. Now efforts are made towards development of another platform, Comet Global, which will be also online, free. And a derivative tool called C-Planner gives regional averages values for adopting standard conservation practices. So the Comet Farm and the C-Planner have current applications in the US to support USDA programs, for example, or carbon farm planning and other carbon offset protocols. There is another method for carbon offset projects in Alberta, which operates under an extensive set of policies, rules, and standards. The conservation cropping protocol is the base for this method. And it's a revision of the 2012 conservation cropping protocol in Alberta, upgraded over the years from the previous tillage system management protocol. This protocol focuses on sequestration of additional soil organic carbon attributable to a change from conventional to no-till, and also for reduction in summer fallow. The protocol uses Canada's National Emission Tier 2 methodology, which developed soil carbon sequestration coefficients based on measuring and modeling local crop rotations, soil landscape types, and interannual climate variation for geospecific polygons in the National Eco-Certification System. So these are the main or well-known soil organic carbon estimation methods for carbon offset projects around the world. And I will be glad to answer your questions if you have, if you need more details. You can email me at my professional email. And thank you for your attention.
So hello, everybody. My name is Ceschia. I'm a senior scientist at INRA, and I'm located in Toulouse, working at the Center for the Spatial Studies of the Biosphere. And I will present you the SAFYE-CO modeling approach that is based on the use of remote sensing data. What we are seeking, what we are looking at is trying to estimate is the change in soil organic carbon content associated to some agroecological practices or corresponding to different kinds of crop rotations, and we are mainly interested in concerning the agroecological practices in the effect of cover crops that we try to address with our modeling approach in order to calculate the carbon storage effect. But the thing is that we tried to develop a large-scale multi-criteria diagnostic modeling tool, but that is working at the plot level in order to analyze cropland ecosystem services such as biomass yield and also, of course, carbon storage. And the thing is that we need to calculate the biomass and the yield as some of the components of the carbon budget. And we try to identify then the impact of some management practices on the carbon budget. That's why we developed the SAFYE-CO model, which means the simple algorithm for fluxes and yields estimates. So why are we doing this now? It's because there is a new generation of satellites at high resolution that are covering all the globe, that are free. So we mainly work with at the moment with the Sentinel-2 satellites that are optical satellites that allow us to measure some reflectances, and from there we derive different sorts of products, such as the leaf area index that we will and the land cover that we will use in our approach. And the question now is, how can we use those remote sensing derived products to calculate specifically here the carbon budget? We started working on that more than 10 years ago in southern France, thanks to the Spatial Regional Observatory that started in 2002. And this area of study is part of two international networks, the JECAM and ICOS network. ICOS is a network of flux towers that allow to measure continuously CO2 and other greenhouse gases net emissions. And we did also, since 2006, several intensive field campaigns in order to measure biomass yield, leaf area index, soil moisture, in order to validate the variables that are estimated by the model. And we use the continuous CO2 and water fluxes measurements at our two flux sites that are Oradé and La Masquère in order to validate the flux components of the model. The modeling approach is rather simple. It starts with the use of the satellite products, either coming from optical or radar satellite, in order to produce some crop maps, or you can use also some LPAs data for Europe, for instance, with some that give you the contours and the type of crops that is located in different plots. From this, we define some specific crop parameters in the model. So we have different parameters for wheat or for maize, for instance. And then as input in the model, we need some climatic data, global radiation, temperature, rain, and eventually some soil maps in order to estimate the available soil water content. There are different versions of this model. It was built on the original SAFYE model that was estimating only biomass and yield, and later versions also allowed us to estimate evapotranspiration by coupling this module with the FAO 56 water budget module, and the latest version also estimates the CO2 fluxes and the carbon budget. So how does it work? Well, we have those input in the model, and what we will simulate is leaf area index, biomass yield, and the CO2 and water fluxes. But in order to force the model to reproduce properly the development of the vegetation, of the crop, we will compare the leaf area index that is observed by satellite with the one that is modeled by the model. And by comparing these satellite estimates and the model estimates, we will calibrate, we will force the model to reproduce the observed dynamic that is shown by the red dots on the figure. So the model will progressively converge to reproduce the dynamic that is observed by the satellite. And that will allow us to have correct biomass yield estimates as well as CO2 fluxes. And then we need different kind of data in order to validate the different components of the models. So regional statistics concerning yield, for instance, of yield map coming from yield monitors, some national inventories or regional inventories concerning yield or the JECAM network. And for the validation of the CO2 fluxes, we use the flux measurement that are available from networks like ICOS, or at the global level, we plan to use the FluxNet network when we will apply it at the global scale. So just to give you an idea of the performance of the model and of the variables that we are simulating. So the model is first simulating the gross primary production. So the model is in blue and the observations are in range red. It simulates also ecosystem respiration, which is the sum of autotrophic and heterotrophic respiration. And it simulates the net ecosystem exchange, and we have fairly good performances for estimating the net ecosystem exchange. And by integrating this net ecosystem exchange over a cropping year, we will use this information to calculate later on the carbon budget. Here on this slide, you can see so the plain bars are the field observations, and the dashed bars are what is modeled by the SAFYE-CO. So I present here some calculations of the carbon budgets and the components of the carbon budget for 8 years of winter wheat at our two sites, Orade on the top and Lamaska on the bottom. Orade belongs to a cereal farm, so only the grain is exported and no organic fertilization. And at Lamaska, the grain plus the whole above ground vegetation is exported, and there is some organic manure, and that's why you see for Lamaska some black large black bars that corresponds to the carbon input as organic manure, and you often see larger carbon export, the CX term, that corresponds to the biomass that is removed at harvest, and those terms are larger often at Lamaska than at Orade. The first bar on the left, the NEP, it's the net annual CO2 exchange with the atmosphere. And in order to calculate the carbon budget, you need to sum the NEP, the amount of carbon that is brought as seeds and or organic manure to the field, plus the term of the carbon export at harvest. And the sum of those three terms gives you the carbon budget. So you see that the model performs relatively well in estimating the NEP, and we sometimes have a slight overestimate of the carbon export term, but in general they agree well, and we have rather good estimates of the carbon budget in the end. What I didn't mention is that for the carbon input term, as we cannot estimate that by remote sensing, we provide to the model the amount of carbon that is brought as organic manure. Also, the uncertainty of the carbon budget may appear rather large sometime, but what we have to be aware of is that one of the main uncertainties is in fact on the yield that is provided by the farmer, because often the yield corresponds to an average over several plots in the farm. Indeed, when we collected, we did our own yield measurements by manual sampling, and we compare that with what the model is able to reproduce, we have better estimates of the yield, which improves the carbon budget. So what the green bar shows, it's the change, it represents the change in soil organic carbon in the soil. One of the our approach that is only based on remote sensing does not require any data on management concerning fertilization, sowing date. It has no soil organic carbon module compared to other models, and in spite of that, because the satellite forces the model to reproduce the true development of the crop, we have, as you can see on the figure on the upper left corner of the slide, some rather good estimates of the net CO2 flux, cumulated net CO2 flux dynamics compared to other well-known models like the Orchidea, SPA, and so on. And you see that when the weeds development are accounted for, because they are seen by the satellite, it improves the estimates of the net CO2 flux, and therefore it improves the estimates of the carbon budget. And it's only with the remote sensing approach that you can take into account those events. The other modeling approaches do not allow that, and of course, in a similar way, the satellite can take into account the development of spontaneous regrowth, or of course of cover crops and their effect on the carbon budget. And that shows the power of remote sensing for constraining this crop model and allowing him to take into account what occurs after the main crop is harvested. So those are some examples of the maps that we can produce for several variables that are simulated by the model. So for winter wheat, 4 different years in our area near Toulouse, it shows the yield, the carbon budget, and the net CO2 flux, and how it varies from field to field and from year to year. So there are some limits to this approach. First of all, it's only a diagnostic approach, but we can test some scenarios, such as accounting or not for the regrowth events or cover crops that grow after the cash crop. We can also simulate what would be the effect of exporting straw or burying them in the soil. Right now, it's only based on optical remote sensing data, but when we want to address areas that are rather cloudy during the crop growing period, we may have to combine those optical data with some radar, like the Sentinel-1 data, in order to overcome this issue. So this is some work that we are doing within the frame of the European project that is called SenseAgri. And of course, this modeling approach is not well suited for areas with animal farming, because it is impossible with the satellite at the moment to quantify the amount of organic fertilization when it is applied, and difficult also to identify whether straw are exported or not for cereal plots. So those are the main causes of uncertainties on the carbon budget estimates. But this approach could be improved by combining it with some inventory data at the field scale, like by using the IAX, the next generation of the IAX data that the European Commission is using. Okay, and as a conclusion, This approach was developed first in the perspective of generalizing it by using some Sentinel data products and by using some networks of observation like JECAM and ICOS. It has some limits, what I just mentioned. And also there are some challenges because in order to run the model over large areas, you have to deal with huge amount of remote sensing data. It is well suited for assessing the effect of straw management and cover crops on the cropland carbon budget. And we have already tested the transposability of this modeling approach with the previous versions of the model, the one that were simulating yield, biomass, and the water budget. And next is to do the same with the SAFYE-CO version over larger areas. So right now we are applying this model to other crops than winter wheat. We are using it for maize and the sunflower, for instance, in order to simulate some crop rotations. And keep in mind that this is a research tool, and it still needs some improvement before it can be used in an operational mode for mapping the carbon budget. Thanks a lot.
So, hello everybody. I hope you all can hear me. My name is Antonio Bispo, and I'm at the head of the InfoSol unit at INRA. So InfoSol is in charge of national soil survey and soil monitoring programs. And we are managing the National Soil Information System. So I will present you why we need soil data for MRV methods. And I will mostly focus on soil carbon. So first of all, why do we need soil data? First one, because you all know that carbon dynamics in soils will depend, of course, on climate, on land use and land management, but also on soil characteristics. That means you will need the amount of carbon, but also of nitrogen, the pH, the amount of clay, if the soil is hydromorph or not, and also if you have information about the biological activity. So we need soil data because we need to initialize, parameterize, or validate models, and then this will allow you to simulate carbon dynamics. But also you need soil data to calibrate remote sensing measurements. For example, if you want to use remote sensing. Then if you need soil data, where will you find soil data? Of course, you have global databases, and I indicate you two major databases. You have the ISRIC databases, and also for Europe, LUCAS topsoil data. And I put on my presentation the links at the bottom of the page. But also you have national databases. I hope you all have national databases for data on soil parameters. And I will focus now on the French example and on the French situation. For France, we have 4 main soil survey and monitoring programs. So that means that we have 4 possible databases. And we have 2 main programs that aim to improve soil knowledge and monitor soils in France. And we also have 2 databases, and the aim of developing those databases is to capitalize soil tests requested by French farmers. And all those programs are made under the supervision of INRA, but also of the Scientific Interest Group on Soils. It's a French organization that involves 2 ministries, the Ministry of Agriculture and Environment, 3 research institutes, and INRA is part of, and 2 national agencies. It's the National Agency for Environment, but also the National Agency for Biodiversity. And the aim of that scientific interest group is to survey and monitor French soils, to organize and store soil samples and soil information, to give access to soil information, and to support public policies. And in fact, InfoSol acts as the national coordinator for the survey and the monitoring programs. So I put the internet website of that scientific interest group. I will quickly go through the different programs. So the first one, it's the soil survey program, and in fact, you can see in the map green points and red points. Red points are the soil profiles, meaning that we have data on soil on that points up to more or less 1 meter. So on that points, we have a soil sampling strategy, and we have analysis linked to that point. And the green points are just topsoil observations, meaning sometimes we have an information, an analysis, but on most of the case, we have just a very quick description of the soil. So it's just an observation. And as you can see for France, the situation is very diverse. Depending on the area, you have you have some areas where you have a dense information, and other areas that are more or less blank. You have quite no information on that area. About soil, we have quite no information on that area. And I just look at the databases, sorry, and I take the number of carbon analysis, the topsoil analysis, depending on time. As you can see, we have quite old data on that databases, middle of the 20th century. And we have also new data coming from last year analysis. But as you can see, more or less 70% of the data are before year 2000. So it depends, and as you see, you have different kind of information across France, meaning areas very dense and areas where you have quite new information, and also quite old information. The second database we can use as for France is the soil monitoring network. It's called RMQS, and the aim is to monitor soil quality and detect soil changes. And so we sample more than 2,000 sites every 15 years, and it's based on a grid. And on each point, we describe the status of the soil, meaning that we take a sample and we make a lot of analysis on that sample, and also we record the management on each site, and all the data is georeferenced. And we had a first campaign between 2000 and 2009, and so we have near more than 2,000 soil carbon analysis in that database. And we are now we are still ongoing on the second sampling campaign, and we are performing more or less 200 sites a year. And those data were used to define the national carbon stock for soils. So we provide that map, and those data, as it was said at the beginning, were used for IPCC reporting, and they are now used as the reference for France. And the last database, it's called, it's a soil test database. It's the idea of capitalizing existing data. I mean that each year farmers make analysis. They ask laboratories to make analysis to manage soil fertility. And so what we are doing is that we are trying to convince the laboratories to give us the data, and we put all the analysis, all the tests in a database. We of course check the validity of the data, And then we use that all that data to follow, in fact, the fertility of French soils. But not all the data are georeferenced. And in fact, as for the two previous databases, I show you here the number of carbon analysis. You generate the topsoil only. We are nearly 2 million analysis on that database about soil carbon. But as you see, it's depending on the year, but we also have two different methods for that analysis. So the main issues when you want to use all the data in the different databases, first of all is to access to that data. Usually it's possible for research purposes, so we have no problem to access the data to make research. But it's very difficult then because not all the data are open. In fact, it's depending on the country regulations, georeference data may be considered as private or personal data, meaning that you should ask first the owner to let you access to the data. So it's a huge difficulty because, as you see, we have quite old data in the database. So finding the owner is maybe a huge challenge. So yeah, for some applications, it may be difficult to access to those data. Then it can be difficult to compare the data sets because you have sampling designs, sampling depths, or sampling methods that are quite different depending on the database, depending on the program. You have different analytical standards. I'll just show you the difference between in one program. You may have different kind of methods to analyze carbon, just for carbon. You also will have different units in the databases, in percent, in gram by kilogram, gram by square meter. And sometimes you will also have the bulk density, but very often you don't have the bulk density. And finally, if you want to use and to interpret the data, sometimes you don't have any idea of the land use and of the management of the soil. With very few exceptions. I told you about the soil monitoring program in France. We collect that information, but for all the other databases, in fact, we don't have the information about, sometimes we have the land use, but not the management. So it may be difficult to use that data. Even if you have access to that data, it's difficult then to use. And as I already told you, we also have all data. For France, more or less 70 to 80% of the data were collected before 2010. So you can imagine that your carbon in your database is maybe very different from the carbon actually in the field. For Lucas soil, the data available is for year 2009. And the ISRIC databases that I showed you just at the beginning, it's a global database. You can see the range of the data, meaning that the first data is from 1980 and to then 2013. So you can see you have very different kind of data on all those databases, and usually it's not taken into consideration. So why to ask for new data? Of course, you should, if possible, collect existing data. What we are doing now, collecting the soil tests that are performed by the farmers. But I think MRV methods should also ask for new data. Of course, we can think about new methods to use the existing data to produce maps and to optimize the sampling design, the sampling schemes after. And we must also organize data collection. That means the sample collection, but also the analysis, so that we can compare all the data at the end of the day. And we also need to collect the metadata, land use, of course, but also the management information. And all that will give us robust data for model initialization and parametrization, carbon dynamics, and also remote sensing calibration. So thank you for your attention, and I can answer questions if you need.
Yes, thank you. So I'd like to provide a brief conclusion for this webinar by citing a paper that we have recently produced for global change biology with Pete Smith and a number of colleagues. And actually, it reflects some of the elements we provided that could contribute in the future to an international scale monitoring system for soil organic carbon. So central to such an infrastructure would be benchmark sites. And in those benchmark sites, we are going to have long-term field experiments with resampling of the soil, looking at the soil organic carbon change over time steps that could be like 10 years. So after 10 and 20 years, you could ground truth the changes in stocks after also changes in activities. You could also have some spectral data on the soil to look into those changes and compare your spectral data with the ground truthing. We need to have activity data that need to be monitored and that could be reported also. So these are the management data. They are about also the land use and land use change. They could well be self-reported. In a number of countries, we have that reporting for the national, or in our case, for the European authorities. And as you can understand, when you have this ground truthing and when you can translate this into spatial data sets with the climate, with the soil, and the land cover, remote sensing brings you a verification of the activity data. So you could tell, for instance, what are the crop rotations, what are the sowing dates, what is the duration of the vegetation cover annually. And these are the inputs that can be used to run models. But further, with the remote sensing, you can have estimates of photosynthesis, and therefore you have the entry point of carbon into the system. When you combine those elements with the benchmark size, the long-term, possibly shorter-term experiments, you can actually have an infrastructure that could calculate over space and time the soil organic carbon changes. So this is a perspective we would like to bring, because essentially we tend to believe that it will be needed, given the magnitude of the challenge for climate change, and also for land degradation and for food security, to bring together those different elements to construct an international scale infrastructure for monitoring soil carbon. And this would open large perspectives in terms of contribution of the landscapes to the overall goal of creating carbon neutral systems and a carbon neutral economy. So thank you, and I think we will take some questions. Yes, thank you, Lini, for your question. I'm not really able to answer your question, but I can just mention that we have a European funded project which aims at better coordinating research on soil carbon sequestration, which name is CIRCASA. And in this project, we will try to create an international research consortium. And so far, we have a draft strategic research agenda that we circulate to all our partners. And in this draft, we see, and it is more a vision, that we need to create such research infrastructure to extend those modeling methods to a national scale, but also project scale soil organic carbon change. And as I tried to introduce, this would really need a combination of benchmark sites, agricultural practices, soil data, climate data, and also having the remote sensing, at least for the photosynthesis, but also for the changes in land management. And for instance, I'd just like to say that a first proxy to understand if we make progress or not on soil carbon in agriculture in arable crops would be to have an estimate of the changes region by region or country by country of the duration of the vegetation cover. Because if you have a shorter vegetation cover, it's quite likely that you will have a decline in your soil carbon. If you increase the duration of the vegetation cover, it may well be that you have also an increase in the soil carbon, because just vegetation is a major input for soil, for carbon. So that's just one example of things that we will start. And we would like to show, let's say, this proxy. We would like also to make a proof of concept to show that this can work in pilot areas. Maybe Eric, you could explain that there are such pilot areas. And then to explain what is needed to bring this to the global scale.
So concerning the areas we have started to apply this approach with the original version of the model, it was applied in southwest France, in Morocco, Tunisia, and in Mexico. The SAFYE-CO version, where it has been applied so far only in the southwest France, sorry. And next, we will apply it, we will use it in Italy, Spain, over, let's say, areas of 200 by 200 kilometers, something like that. In central and northeast France also, and within the frame of the Climate Kit project, we plan to test the model also in Switzerland.
Yeah, thank you, Eric. Yes, thank you, Oliver, for your question on maybe the hotspots, if I may call those, of soils accumulating organic matter. What is a general agreement usually in the literature, but also in a national study we had in France, is that the potential for soil carbon sequestration is, as you say, bigger when initially you have been depleting your soil carbon during the last decades. So we see a very clear correlation, which is a negative one, between the initial carbon stock and the potential for soil carbon sequestration. And so this plus other consideration on soil type and on climate can certainly guide us on what would be, let's say, the most efficient deployment strategy for soil carbon sequestration. Because we know that in some instances where you have already a high stock, what is essential is to preserve that stock. But the possibility to increase the stock is not very big, because you would need to still increase your vegetation productivity, or maybe to have a lot of manure to apply, but we know that this is sometimes not possible. And in contrast, if you start with, let's say, an area where the stock has been depleted and we have a lot of bare soil during the year, then it gets quite simple to have cover crops or better crop rotations and or grasslands. And in that case, you would quickly reestablish a much improved soil carbon stock.
I just add a point. We know that the soil type will also influence the carbon storage and the amount of carbon in the soil. As you said, the soil, you ask us about the soil texture, for example, and we know that sandy soils and silty soils will not react the same way. So we know that the soil type is very important.
Yes, indeed, yes. Maybe we could also try to answer Viridiana's comment. Well, thank you, Viridiana, for pointing at the Lucas strategy, which is the European Joint Research Center strategy to sample soils? And should we also have national inventories? I think I would like to ask Antonio to answer about this, because it is obviously an important question for the soil surveys.
Yes, in fact, you have two different sampling strategies for LUCAS soil and for the national monitoring program in France. So we have two different kind of strategies. And I think we are now comparing the data with EU, with the JRC. We have a program when we are trying to compare the results from LUCAS and the results from the national programs. And maybe we will not have exactly the same results, because, as you know, LUCAS, for example, do not sample mountains. So it means that we know that in mountains, you may have big amounts of carbon, because you have the land is not managed, and you have no cultivations in high mountains. And we know that the carbon stocks in mountains are quite high. And in fact, we may find differences between the two monitoring systems. So actually, I'm not able really to answer if it makes sense or not to keep the two. We need to compare before saying that we can skip the national level or not. Or maybe we can try to harmonize both systems, because they do not sample exactly like we are doing. They just sample the topsoil, but we also go to 1 meter depth, for example, for the national program in France. So it's not exactly the same. So we need now to compare those data sets and to see if they are equivalent or not. Actually, I'm not able to answer that question, but the fact is that we do not, the strategy is not the same. So it may end with different kind of results. I don't know if it answers or not your question.
Yeah, thank you, Antonio. Yeah.
Maybe Melissa?
Yeah, Melissa. So thank you for your question. Yes, we are working with the ROTC model. There are many other models. I just try to introduce in a general way this issue, but maybe I would pass it to Eric or to Gecica. There is usually a trade-off when you want to get operational calculations of changes in stocks through a model. If you work with a complex model with many parameters and parameter values, then the uncertainty is quite usually linked to the value of those parameters. And you may end up with difficulties in making sure that you know of all parameter values. In contrast, if you work with a rather simple model, what may happen is that the uncertainty is more with the equations. So if you have a small set of equations, they may not be enough to describe with accuracy the processes that are happening. So it is easier to parameterize because you have less parameters, but you have a structural uncertainty in your model that may also create a problem. But these are really sort of general concerns. And my personal feeling, but I think there are some papers intercomparing models also, is that ROTC is a rather good compromise if you want to get operational projections, assuming you have all the input and output of carbon to your soil, so you know how your soil is, let's say, supplied with carbon, and you know also the texture and you know the climate and so on. Basically, they were more complex and more simple models. With the more complex models, it is difficult to know all parameter values. And with the more simple models, it's difficult to know if your equations are working in your conditions because they may be too simplistic. But so I was just saying, yes, ROTC is a good option. It's rather a simple model. And Century or Descent are more complex models, but they've been also parameterized very carefully in many locations. But maybe others would like to complement.
Yeah, I would just like to add that there is a guideline wrote by the LIP, which is a consortium of scientific experts on soil organic carbons, offering guidelines for a choice of a model to from a 1 to 3 level as it is for the IPCC guidelines, but for a choice of a model, I will give the link to that paper in the Q&A and maybe by email with the other information at the end of the webinar for those interested.
Okay, so thank you all for your questions. I think we will try to send you some further information by email. And it was great to see your interest on this question. And we hope to be further in touch with you and to maybe organize further webinars on those issues. Thank you very much. Bye-bye.